Thank you. Okay, thank you for the nice introduction, and I would like to thank the organizers for inviting me in such a good conference. So today I'm going to talk about this topic, which is an mathematical applied side of my study. Okay, so this talk is based on the recent research supported by JST Foundation. Like, and this is the title of this fund. But these are the collaborators with, so they are contribute to these results. Okay, so let me first, the mathematical foundation, mathematical theory we are going to use here is a topological flow data analysis. This is a different branch, another branch of topological data analysis we are now developing. So in this talk, I like to say this topological flow data analysis as TFDA for short. Okay, TFDA is a mathematical data analysis that extracts topological features of fluids through orbit and generated by 2D vector fields based on the Poincare-Hopf theorem and the Poincare-Bendixson theorem. So by this TFDA, the global configuration of a topological flow structure is converted to a planar tree. I would say partially cyclically ordered through tree. It's too long, so I would say this is COT for short too. And also it has some very convenient symbolic representation, say COT representation. By using this graph and symbolic representations, the flow pattern is decomposed into several topological orbit structures, which I will say topological modes. I'm going to explain later for detail. Anyways, so this topological mode decomposition is applied to vortex identification problem in many fluid problems. So this is a topological stuff. So it is very good at extracting some qualitative information from the data, but our method can also extract quantitative information associated with topological mode. This is very convenient mathematical tool to obtain some qualitative and quantitative information for the data. Okay, so the main point of this study is to introduce the topological modeling of transient flow dynamics. So in which we are going to, which the evolution of flow dynamics is reduced to a discrete dynamical system among these topological modes. The main purpose of my talk is to give you an idea how we construct topological models and the analysis. Okay, so let me first give you a small, brief overview about for the TFDA. For the most simplest case in the 2D structurally stable Hamiltonian incompressible flows. So in here, we assume that the vector field is Hamiltonian, in which U and V, the velocity component U and V are recovered from a scalar function, we say the stream function from the, and then this U and V are recovered from this form. So this is why we say Hamiltonian vector field. So we are now interested in the particle orbit as vectored by these velocity field. So then we are tracking the topological structure of level curves of the Hamiltonian, which are called streamlines. And so also in addition to this Hamiltonian assumption, we have made another assumption called structure stability. So this is where the topological streamline patterns remaining unchanged and any small perturbation of vector field in CR topology. So with this very simple mathematical assumption, we could show that the streamline of any structurally stable Hamiltonian vector field in the uniform flow consists of the following four local orbit structures. So these are the four categories of local orbit structures. The first category is homoclinic saddle connections, which are the saddle connecting two self-connected saddles. The second category is a boundary saddle connections, connecting a boundary saddle on the boundary and the saddle at the same boundary. The third category is a boundary embedded in the uniform flow, which is a uniform flow. A streamline is attached to the boundary, then detached to another point on the same boundary. So the last category is an SS saddle connection embedded in the uniform flow, having one homoclinic cycle. So for those topological structures, we assign some special symbols, say the COT symbols, to describe local topological orbit structures. For instance, for this category, we assign the COT symbols V. Then the plus minus sign represents the flow direction along the homoclinical. So in this example, we see two counterclockwise homoclinic orbit. So then this is COT symbols for this structure is B++. In the same manner, we can assign each topological pattern with the flow direction as B plus minus C plus and so on. So once we have obtained some characterization of local orbit structures, we can convert the global topological structure of these local orbit into a tree structure. This is how we do. So this is an example for the snapshot of the flow simulation where the flat plate are embedded in the uniform flow. So you can see a very complex and vorticity structure here. So then we can extract from this data the topological field, topological structure of these streamlines. So which looks very simple, but I'm going to convert this topological structure into a graph. Okay, so first thing we need to do is to identify the new fundamental flow structure of this flow. In this case, with the fundamental basic flow is a uniform flow. So next thing we need to do is to find a structure that are embedded in this uniform flow. In this case, we see a one boundary attached to the flow line and detached from line. This is A2 structure. So then we can create the A5 to the child node as A2. This is a graph, direct graph is constructed. So next thing we are going to do is identify another local structure attached to this boundary. This is here. This is a clockwise boundary saddle connections, which is called C minus structure. Then we, as a substructure of this flow pattern, we create the graph from A2 to C minus. Then we are going to read the inner structure enclosed by this clockwise saddle connection. Then we have one B minus minus here. Then another C plus is here. So then C minus has B minus minus C plus structure as internal structure. Then we create the edges. So in addition to that, this B minus minus structure contains the two elliptic centers going the clockwise direction, which is assigned sigma minus as COT symbols. So now we have no other topological structure to be identified. So then we stop this procedure. So that's, you say, the global structure of this flow pattern is converted in this kind of the trees. This is how TFD works. Right? Okay, so this is the output of the TFDA. So we are, for any streamline patterns, for the structure stable to the Hamiltonian vector field can be converted into this kind of graph, which is COT. So, but it is hard to describe this graph structure every time I show you. So we have another very convenient expression for this graph structure. This is called the COT representation. This is the COT representation for this COT. So this goes as like this. So A5, which is a root structure, contains 4 child nodes. That means we have A2, A2, A2. Now, then there are no other structure embedded in this structure, but we have another structure as embedded, A2. There are 3 C plus structure and 3 C minus structure are embedded, which is described as one line, C plus, C plus, C plus, C minus. So then this C plus contains a B plus plus, this B plus plus contains C plus sigma plus plus. Then this is a sequential letter representation of this graph. This is a much more convenient way to describe in the talk. So anyway, so it is mathematically shown that the correspondence between the topological structures of a streamline pattern with the COT is 1-to-1. So that means we can encode the topological information into a graph, then we can recover some topological information to the streamline patterns. So for those who are familiar with different and discrete geometry for the 2D structures of Hamiltonian flows, COT, this one, is equivalent to the wave graph of the Hamiltonian function. But it includes the information on the flow direction and the global flow structure information. And we also note that, as I shown later, the COT becomes different from the wave graph when we consider more general 2D vector flow, such as compressible flows, as I'm going to explain later in the application section. Okay, so this is the basic of the TFDA. So you may I hope you understand what we do. We convert the flow pattern into a graph, and the graph has some topological information. Okay, so we apply this idea to create a topological dynamics modeling. So the target of this talk is a rate-driven cavity flow. This is a incompressible flow inside the rectangular domain omega here, then have enclosed by four boundaries. So the boundary condition of this flow is given here. So the three sides on the cavity, the flow field is always zero. But on the top side, which I say a lid, which is the lid of the cavity, it's moving at a constant speed from the left to right. So this movement can generate a steady boundary condition expressed like this flow. So because of this injection of this movement of the lid, the flow generated is this direction. So so we are going to solve this Navier-Stokes equation with this boundaries subject to this boundary condition. Then we can observe the time evolution of this flow. So here is one typical example of this flow. So then this is a cavity. So you can see a big clockwise rotational flow associated with three corner eddies. The three corner eddies change its topology as time goes. Okay, so we are going to observe what happens in this flow. So here, this is a time evolution for the Reynolds number is 14,000. So as you can see, the topological changes observed in the three corners. But when we observe the energy of this evolution, the energy is oscillated periodically. This indicates that this is a periodic motion in the physical sense. On the other hand, when we increase the Reynolds number from 14,000 to 16,000, the pattern looks very similar, but when we observe the energy, this looks asynchronous. It looks very chaotic one. The purpose of this present study is by using the TFDA analysis, TFDA, we are going to detect the transition from this pattern, chaotic pattern, laminar state to chaotic pattern. So this is this is a problem we are going to consider by creating a topological model, dynamics model. Okay, so the first step is to convert the flow pattern of each time to the COT. So here's an example. This is a snapshot. So I have expressed in the second slide, we have to identify the basic flow. So in this case, this is about the flow inside a bounded domain whose boundary direction is going to clockwise because the flow goes like this around the boundary. So then this is a beta phi minus, which is a COT symbols for this of this flow. And then we identify a big clockwise rotational structure in this center. So then we create an edge as sigma minus here. Then we, for the three corner edges, we found the three boundary saddles, like here and there. So when we want to identify the location of this flow structure for the boundary saddle for this one, which is C plus, we enumerate number 0. 0 means corner edges. And boundary saddle connection at the left corner. For the left bottom corner, we see C plus 1, which is here. This is C plus structure going to the counterclockwise direction. Then another one is the right top bottom corner is C plus 2. Okay, so then we are going to read the inner structure for each edges, corner edges. For instance, when we focus on the C plus 1 structure, we see another B plus inside here, containing the two elliptic centers. And also we have another clockwise boundary saddle connection, which is represented by C minus as an inner structure of C plus 1, then C minus structure contains the elliptic center going clockwise direction. Then we can have the graph structure associated with the corner edges at the left bottom corner. In a similar manner, we can assign this graph structure for each corner edges. So this is a code for this time. Okay, so the main idea is we consider this COT representation as a topological mode decomposition. I mean, this is, as you see this graph structure, The subgraph structure follow the C plus and sigma minus represent the topological structure of this local corner IDs. In the similar manner, C plus 1 and these subgraph structure can represent the topological orbit structure for this corner ID at the left bottom corner. So that in that sense, we can say that for each corner IDs, this structure can be converted and is regarded as this sort of the graph structure as a top mode. So then we can this kind of COT representation as a mode decomposition associated with the local orbit structure. So in terms of the COT representation, which plays a very important role for the time analysis, this combination and arrangement of C plus 0, C plus 1, C plus 2, which are the topological modes for each corners, plays a very express the topological mode in the one line. So in what we are going to, in order to create a dynamic modeling, we focus on this arrangement to express the topological features as some a snapshot of this evolution. Okay, so then we are trying to apply this TFDA analysis, topological mode decomposition for the time evolution. So we are going to sample from the numerical data every 10 steps after a long transient time, 5,000. Then we enumerate the TK as a case state, like this. So this is the 6 panels and the different topological features. So we are going to observe how this topological structure changes as time goes. So this table shows a change of a COT and topological mode. For the time from T0 to up to T277, we have the COT representation, which is equivalent to that one at T equal 140. So then you see a 3 simple topological modes, C plus 0, C plus 1, and C plus 2. During this time interval, the COT never changes, because then COT is for the structure stable, Hamiltonian vector field, and remains unchanged from the topological point of view. So, but at time 278, this pattern changes abruptly to this pattern. So in which you can see the double C plus 0, which has this here 2 boundary connection at the top left corners, then but the other one that remains the same. So this is another topological mode. So then we can identify this as a different one from the panel A. So this situation continues up to the time 318. Then at 319, the pattern changes drastically from that pattern to this one. Then we can see at the top left corner, the topological mode is given like this. It looks very complicated. And then after 398, this pattern disappears, and the topological mode on the left top corner becomes very simplified. But we still have the 2 topological modes for the left bottom corners. But then this bottom left corner changes and changes in a complicated manner as at time to 425. So after time, the 498, this topological mode decomposition can be returned to the original one. So this indicates that for the time evolution for the Reynolds number and 14, we found one cycle of the topological changes in terms of COT representation. Okay, so by observing the topological and local topological mode, we can estimate how the pattern changes. So here's an example. The topological mode for the top left corner, it changes from C plus 0 to double C plus 0. Then this is going to this kind of structure, then disappears. So we have a mathematical theory how this change occurs at a topological point of view. On the first step is due to the emergence of a degenerate point at the boundary. So then we create another new boundary saddle, then we increase the number. So from this one to that one, we see this kind of transition. For 2 boundary saddle merges, like here, this is an topological structurally unstable orbit, having a heteroclinic orbit like here, but it changes to this topological structure, stable structures, which is T and this one. Okay, we have the C plus and B plus minus contained and C minus here. So this transition is going from this one to that one through this marginal state. So that one, so from the transition from this one to that one, we need to do two steps. One is a disappearance of this topological structure by merging two ellipse centers into one. Then after that, because of the existence of the rotational flow, the bottom boundary saddle catch up with the top one, then merge here, then detach. So then we have only one isolated boundary saddles and at the last. So this is an expression how the pattern changes in topological point. Okay, so now we're going to create a topological modeling by creating a transition diagram. So we are going to track the change of a topological mode in time by the following 4 steps. So applying a TDA to the flow pattern at each time. So we extract a topological mode of the corner edges, which is expressed by C plus 0, 1, 2 in the copy representation. So next is nothing as long as the mode remains the same, but when the mode changes, we create a directed edge between modes before and after the change. So repeating this procedure for the whole evolution, we obtain a directed graph representing the transition between the modes. So here is an example. Here data we have. So for up to from 5,000 to 5,277 steps, the topological model is C0, C1, C2, but at 228, we have C plus 0, C plus 0, C1, C2. Then we can create the edges from C plus C1, C2 to C plus 0, C plus 0, C plus 1, C plus 2. In a similar manner, every time we observe the change of topological mode, we create the edge. So then repeating this step for the final step, we find this kind of pentagonal transition diagram. So in that sense, we can reduce the evolution flow pattern is converted into a discrete dynamic system. So we are going to apply some data, we applied some analysis for this graph structure. The first thing we are going to do is a graph analysis. So we can, from the transition diagram, we can obtain an n by n matrix M, which is a transition diagram as follows. For each node I of the graph, we compute the number of transitions to the node J, which is not I, say Cij, so for every node. So note that for this construction, the Cii is always 0, since we do nothing, the transition from the node I to itself when constructing transition diagram. So by normalizing this component by the whole number of transitions, then we obtain the transition matrix. So for this transition matrix, the eigenvalues of this one provides some information about the discrete dynamical system. Yeah. Non-previous. Yeah. Yeah, for each eye, we create the number. Yeah, degree 1, we add 1 for this one. Yeah, I2, Y, I see. Yes, I'm sorry. Yeah, okay. So, because this is periodic evolution. Okay, so the eigenvalues of this transition matrix have very good information when we regard the dynamics as a Markovian on this graph. Suppose that M has a distinct eigenvalue lambda J and its associated eigenvalue Lj, then the probability density on this graph is Markov process is given here. So where the first term is the periodic part where the eigenvalues on the modulus of the unit circle. On the other hand, the second term represents the decaying mode whose an eigenvalue less than 1. So the information of these eigenvalues give us some information about dynamics on the graph. So here's we are going to apply. So this is a transition graph as I have shown later for the Reynolds number of 14,000. So for this, we are creating a transition matrix. They have an eigenvalue of this is aligned like this. This indicates that the 5 eigenvalues are aligned on the regular pentagon, and which means the dynamics flow pattern has period with period 5, which is very consistent with my intuition. So we can do the same thing for the flow from Reynolds number 14500 and 15500. For the case of 14500, we have the 6 nodes going around. So the eigenvalues becomes like here, we have a 6 and hexagonal alignment on the dynamic. That's still periodic evolution. For the between in the 1475 up to 15200, we have this sort of the singular transition matrix, which has a two triangle attached to the one centers. So the corresponding eigenvalues becomes the 1, 0 eigenvector and 3 equilateral triangle distribution. Up to now, we can have a very simple, almost periodic evolution for the flow pattern. But after the Reynolds number increase after the 50 and the 2050, the situation changes drastically. So here is a case when we consider Reynolds number 15500, as we expect the flow evolution looks very complicated. So the eigenvalue of this transition graphs become here. So this indicates that we have some transition in terms of the graph evolution, the Markov process between this time evolution. In that sense, we can detect the transition to laminar state, periodic state, to a weakly chaotic state. So this is a final state at 16,000. The graph becomes much more complicated. The distribution of this graph and the eigenvalues is much more spread or inside the Trinity circle. So here's another indicator for the average degree of the transition diagram. So it is 1 and 1.7, something like that. Up to this now, so we have a hexagonal, pentagonal, and evolution. But in this area, we have almost 1.5, meaning the graph is in a 2 triangle attached to the bound, attached to the 1 point. But after that, the increasing number of the average degree, this indicates another indicator for the existing chaotic, the very complicated evolution. Okay, so the next analysis we are going to do is an information transfer analysis by using a convergence cross mapping. So we are going to consider in a periodic state. So in this case, in this state, flow pattern changes at each corner as asynchronous. So suppose we interpret the order of the topological changes in flow pattern at the cavity corners as information transfer resulting from the evolution of the flow. In this problem, it is very interesting to understand how a change in pattern at one corner influences the change at corners. So this here is we can have two possibilities of among the causality. The first causality is the recirculation region forms first at the top left corner, then due to the lid movement, and followed by the change of the bottom left corner because of the rotational flow. The another possibility is the C plus 0 at the top left corner edges forms through the vorticity transport from the left bottom corner via the large clockwise rotational flow cavity. So this is a kind of a chicken and egg causality. So we have to determine which was the more likely to be observed. So in order to answer this question, we employ the convergent cross mapping by Sugihara to measure causality among the topological changes. So CCM investigate whether knowledge of one variable is useful in predicting future value another. This is one of the observational causality analysis. This is different from the conventional interventional causality analysis, such as sensitivity analysis. Okay, so here's in this slide, I'm going to explain how to apply the CCM theory, CCM analysis to our topological data analysis. So in order to apply the CCM, we have to vectorize the topological information. So first, we are going to define a state VKI of each corner I, 0 to 1, 2 at each time TK. Then, where the VKI is 3 if the B++ is present inside the parenthesis of C plus I in the topological mode. And it is, otherwise, it is a smaller of the number of C plus I and 2 otherwise. So then we can embed the information of topological changes into vectors. So then we form a state vector at the ith corner using the time delay embedding by here. So that the delay time can be determined and maximizing the accuracy of the autoregulation. I won't explain how to do that later. But anyway, by using the vectorized form state vector, we use a dimensional reduction by using a principal component analysis. Here is the evolution of the first component for the case of 14,000, 16,000. This looks periodic, this looks asynchronous. So we're going to apply the CCM analysis for this kind of time series. So this is the result. So using the delay embedding, so CCM evaluates the prediction accuracy through as a correlation coefficient. So using increasing larger historical data sets until convergence. In a deterministic system, the dynamics of the drivers variable, which is the cause variable, is embedded in the effect variable dynamics. So that means higher precision accuracy of one variable using another stage indicates that predicted variable causal inference, the predictor variable. So this looks very complicated, but it's a very simple result. So this is a correlation coefficient obtained by CCM for the various Reynolds number. So up to the Reynolds number around here, where up to now in this domain, the revolution almost periodic. So as you will see here, the orange one is a correlation coefficient where we see the prediction of C1 using the C0 information. But that means the C0 is the cause and C1 is the effect. The blue one is a prediction accuracy of the C0 by using the information of C1. So this is the blue one. So up to this now, so up to this, these two blue and orange one are the same level of 1. That means we have the similar correlation for both terms. This is consistent with an observation that the evolution is periodic. On the other hand, in the asynchronous stage, we see difference. The prediction accuracy from C1 based on the C0 information is much higher than the opposite one. This indicates that and this in asynchronous stage, the C0 works as a cause of the variation of C1. So this indicates this is the result in the corner changes as top left corners comes first, which is the cause, and then that at the top bottom left. So then by using a CCM and causality analysis, we can I understand the different, kind of causality from the evaluation of topological of the flow. Okay. We still have 30 minutes. So, so based on this, so before I go to the next part, so this is very important. Note that once we have obtained the variation of the topological change of flow patterns, we can convert it to COT and topological mode decomposition, then track the change of the topological mode decomposition in time, then we create some sort of transition graph. So by using the graph analysis and this kind of causality analysis, we can detect some causality and the complexity of the flow dynamics as a discrete dynamical system. This is a very important message for the first part. All right, so we are now going to apply this idea into the more real problem, like blood flows in the left ventricle of the heart. Okay, so here is a problem we consider. This is a vortex identification problem in the heart flow. These two motion pictures about MRI image processing inside the blood flows in the left ventricle of the heart. So this is a heart failure case. This is the same heart, but it's after 1 year dosing treatment. Medical doctor need to find the effect of dosing after the 1 year. So by just looking at this information. So in clinically, many doctors, it is said that disturbances in the vortical patterns you can see around here cause an inefficient flow and worsen heart disease. So the doctors would like to see this kind of vortex structures from this data. And so because the 2D vortex flow structures in this left ventricle play an essential role in describing the efficiency of the blood flow in heart disease. But unfortunately, a few objective definitions of the vortex structures in this data are present for the blood flow stream. So that gives rise to the difficulties in describing the vorticities in this flow image comprehensively in clinical examination. So they cannot use this kind of flow information as to diagnose the treatment efficiency. So this is why we need to identify the vortex structures from flow data inside the left ventricle in an objective manner in clinical medicine. This is the target and purpose of the present application. Okay, the data. The data we're going to use an echocardiograph, which is a more simpler device to measure the heart efficiency. So this is the original image of echocardiography. So on the left ventricle, like measure like this. The probe is here, then they are measuring the section of the left ventricle. So here is an original image. You can see a blue and red regions, which indicates a strong shear appears. But unfortunately, from this modality, we cannot detect whether we have the vortex structure inside the heart. But there's another technology called the echocardiography vector flow mapping. By using this software, they can recover this original flow data, to recover the velocity field inside the left ventricle by solving some continuity equation inside this area. So anyway, so once we have obtained the vector field, then we can reconstruct the particle orbit at the instantaneous particle orbit by using this measured velocity. So now we can identify a large swirling region in the middle of the left ventricle. This is the vortex structure that doctor identified. But unfortunately, it is still uncertain which part of the region should be identified as vortex structure in an objective manner. So to address this problem, we apply the TFDA from a topological perspective. So, but the application of the TFDA for the structurally stable Hamilton vector field no longer applicable because for the technical two reasons. One is the flow in this section is no longer incompressible. So we have to extend a TFDA theory for compressive flow. Another problem is a very characteristic to the heart flow. The boundary is constantly moving. That generates this sort of the transverse boundary condition at the wall of the wall of the left ventricle. This boundary condition is a very unusual situation where we cannot consider in the original TFDA theory. So to solve these two problems, we extend for the first problem, we generalize the TFDA by introducing a new class of vector field called the flow of the finite time. This is a generalized class of structurally stable Hamilton vector field containing the gradient and Hamiltonian components. So we can create in this paper, we can create the similar theory that converts this topological structure into COT like here. I won't explain here, but anyway, so we can, in the same way, by generalization, we still have the COT representation, unique representation for this type of compressed flow. So in that stage, the COT is no longer equivalent to the wave graph, but still express the global topological structure of flows based on the Poincare-Bendix and the Poincare-Hopf theory. So this is the solution to the first problem. For the second problem, we introduce a mathematical idea. So the transverse flow orbit at the boundary are represented by a degenerate fixed point on the sphere by using this collapsing of the boundary. We are going for this is the original data. We see the boundary transverse boundary condition. Then we collapse the boundary into one point by the following equivalence relation. The 2 points are equivalent when they are on the same boundary. By using this equivalent relation, these boundaries are glued into one point at here. And this flow on the disk can make the flow on the sphere. So at this point, the flow profile around this point, this is modeled as a degenerate fixed point, which is named as an n-boundary SSR. So anyway, so by using this transverse boundary condition, the transverse boundary condition can be converted into one degenerate one, the fixed point, then we have no effect of boundary condition. So here is the mathematical theoretical machinery, how we apply the TFDA to the flow on the left ventricle. Okay, so now this is a mathematical model of the flow inside the left ventricle. So this is a red S denotes the spherical surface without solid boundaries. This is the flow domain as a result of the grooving of the boundary. And the flow on S is called the flow phenotype with an n bundle as a saddle if it satisfies all fixed points. Single orbits are non-degenerate except for this glued and degenerate point. The second condition is the finiteness of the limit cycles, and the three all saddle separatists between saddles should be all self-correct. This is a kind of model for the flow in the left ventricle. We can create a new theory for the TDA suitable for this class of vector field. So here is an explanation. So we identify the regular points, the center, and the saddle, and source and sink. And we also need to identify a limit cycle and the limit circuits like here. Then we can say the sink, source, limit cycle, and this and the boundaryless saddle degenerate point can be regarded as a class of SS component. For them, we have considered a one-dimensional orbit connecting a saddle with either of this S component. We say it's SS separatrix. So then the final output of this theory is we obtain SS saddle connection diagram. This is a network of SS separatrices. I'm going to explain using an example. For instance, okay, so the notion of SS separatrix looks very complicated, but this is an example. So this red line connects the saddle to the limit cycle. This means an SS separatrix. This cycle is SS component, and the other one, this is source, is connected to saddle. This red line is also one of the SS separatrix. So in a similar manner, when we connect the saddle to the singular fixed point, this red line is also SS separatrix. We extract this kind of SS separatrices along with SS component. Then we have a network of SS separatrices called SS saddle connection diagram. So here's an example for the SS saddle connection diagram for the data I have shown here. This is a flow field generated by the echocardiography VFM. So then we extract from this data as a topologically identified one. This is saddle connecting the boundary. Here is a sink here. Then this connect the boundary, then detach the boundary. This is a saddle connection diagram for this pattern. So this is said BDV. This is a symbol. This is the notation of this saddle connection diagram for the given velocity vector field B. So here the mathematical theorem, we show that for any flow of finite type with an n bounded saddle, each connected component, the complement of this boundary, this saddle connection diagram is either the following three flow domains. One is a flow box, the other one is a source and sink annulus, here the periodic annulus. So by using this fundamental the theorem, we can do the same stuff as we have shown in the first three slides and the TFDA for that. We can assign the COT symbols for each pattern. So for 2D dimensional structures, we assign the B plus minus tilde for the source sink annulus, the P plus minus for the sink periodic annulus. So for singular orbits, epicenters, sink, and source, we assign a sigma. Then the special degenerate one is identified as infinity plus minus tilde. For P, we assign the limit cycles. So in the structures with the saddle, we have 1, 2, 3, 4, 5, 6 categories. So for which we can assign A plus minus, Q plus minus, and so on. So once we have classified all possible topological structures appeared in this class of field, then it is easy to convert the flow pattern into a tree structure. Here is one example. This is an example. So this is a saddle connection diagram. So we can find a sink structure which is going to the clockwise direction. The COT representation of this pattern is sigma minus tilde minus. You don't care about the symbol, but anyways, this point depends on this one. So this sink structure is a substructure of this kind of red one. This red one is topologically equivalent to this A minus structure, in which we can identify two sink structure, and in between there is one saddle. Here is saddle here, this saddle corresponds here. So then we identify the sigma minus as this sigma minus tilde sink structure, and the other one is a boundary, which is n source, which is a glued degenerate fixed point. Then we create a graph like here. Then this red one is contained in the one of the four regions separated by this topological structure. Then we have this one, that one, that one. Then we can finally convert this flow pattern into this kind of graph structure. This is COT for this class. So we have shown that the flow pattern of the flow pattern finite type with an n-bundled SS saddle is one-to-one correspondence with COT represented here and the SS saddle collection diagram. So this is why we can apply this mathematical theory to the topological flow data analysis was helpful. Okay, so here is an answer for the present problem. Okay, so this is a COT and COT representation given here. So then we identify a certain structure represented by these COT symbols as topological mode for the vortex structure in the heart. So this topological mode, which is a subgraph of this structure, corresponds to this big red region, which is a region of influence of the topological mode. Then it is a domain. The boundary of this domain is given by the saddle connection from this tangent line to this boundary. So that this means that the boundary of the topological vortex structure is now identified. So by using this area, we can quantify the shape and the area and the geometric centers of this domain. So we also, as a result of this, we can evaluate the heart function as a part. So this is a new notion called the TBS, topological vortex structures, derived by the TDA theory we have developed. Okay, so we have now developed a software, looks very not smooth, but we have a severe software that can do this kind of TDA theory. Here is a time evolution of each snapshot of the heart. So we can examine the evolution of this topological flow, topological vortex structure for the 50 healthy heart data. Then we found that there exists a typical topological vortex structures appear in diastole and systolic stage. So these are a typical example. At the systole, when the flow is ejected from this valve, then we can see a big swelling area with a topological vortex structure in the center. And the diastole stage, where the flow is injected from the valve, then we have a pair of the vortex structure, which one is bigger and a small, but this in a section of the vortex ring structure appears. So for any 50 healthy health data, we see this kind of structure appears at this stage. So in that case, we can identify how healthy heart can be described this as the emergence of this typical structure. Then we can say the difference between the healthy heart and the diseased heart. So here's an example. This is a healthy heart, as I showed in the previous slide. You can see a big topological vortex structure represented by this topological mode. So these two patterns are the heart failure case. So for the heart failure case 2 here, C, you can see two topological vortex structures here and there, but they are split, like green region and purple region. And for the heart failure case 1, we see only one topological vortex structure, but it is very small. So as a result of the splitting and the small size of topological vortex structures result in the weak ejection from the valve. That is the cause of the heart failure. So we are now applying this technique to the clinical studies based on the topological vortex structures for heart diseases. Here is one example, which has been published recently in the medical journal. So we are applying a TDA theory to an early detection of cardiotoxicity in childhood cancer survivors. Looks very complicated, but anyway, so answer, since I don't know how to pronounce it, here is one of a kind of the chemotherapy that is good for the child cancer. But this, even if this chemotherapy works well for the child, but it still carries a significant risk of the late onset cardiotoxicity. This is bad. So in order to understand the reason why the karyotogishi occurs in terms of the vortex flow dynamics, we use the TFDA. According to the TFDA, with using a TFDA analysis, as I have shown in the previous slides, we analyzed 90 patients for the category and the normal 1 to the normal 3 class, depending on the age of the patients. And other 90 controls, this is the patient class. This is 90 control, the C1, is then we can compare the difference in a statistical sense. So we take two measures associated with the topological vortex structures. One is the size of this blue region. This is a healthy one. This is non-cardiotoxicity. This is a cardiotoxicity case. So as you can see, the size is very different. The other the indicator for this one is the size between these twin vortex at the diastolic stage. So in this healthy one, you see a very large good flow inflow, but on that here is a heart failure case. We can hardly see a very small and narrow path between two vortex structures. So when we do use this kind of indicator and compare the conventional indicators, then we have some effective difference can be detected by using this topological flow vortex and the indicator using the topological vortex structures. So we are now using this kind of technique to apply many heart diseases and find many new findings by using topological fluid data analysis. Okay, so here's a future plan. So this is we have obtained a flow pattern to cut at each time step. Then we have a time series of the variation of COTs. So when we focus on the topological vortex structure as a topological mode, then track the change of the topological vortex structure, then we can create some sort of the transition diagram, as I have explained in the first part. So we are now trying to convert this kind of flow data into this sort of graph structure. Then we can compare the graph structure, then identify which one healthy, which one is disease. So as a transition graph. So this is a kind of a simple model of heart failure should be constructed by using TFDA. All right, so this brings us to the end of my talk. I have here a snapshot of my talk, of my presentation. Thank you for your attention.